постепенно переходим к нашей звезде, по крайней мере, первой части ивента. Вот. Сейчас мы поговорим с Юргеном Шмидхубером, человеком, который является автором одной из самых цитируемых в 20 веке статей, которая так уж получилась, что про машинное обучение, конкретно про LSTM. Сейчас я перейду на английский, вот, но не обессудьте. Come on, вы же машин-лернеры. So, hi Juergen. I was telling our live stream viewers that you are author of one of the most cited papers of the 20th century, and that from now we'll be talking in English. So, how's it going?
Hello, Alexei. Thank you very much for having me here, and it's all going fine over here. How are you doing?
Great. You see, behind me there is the canonical Russian winter with the snow falling down and with some creatures like reindeer, for example, also listening to our Data Christmas program. So one knows, maybe they'll become authors of some machine learning papers anytime soon.
I have no doubt about that.
Okay, so what we wanted to arrange here is like an interview or a discussion on what is going on with machine learning and AI globally in 2020 and beyond. And let me start this interview with the probably most timely question, like what do you think were the most outstanding use in AI in 2020? And in particular, news which you think were not appreciated enough?
I wish I knew. I wish I knew what was the most outstanding achievement in AI in the last year, but maybe I won't know for a while, because maybe some unknown brilliant guy in India or some other place posted something that will be viewed as big in 25 years, you know. So this actually reminds me of our recent quarter-century anniversary, because 25 years ago we received a message from the NIPS conference. Today it's called the neurips conference in 1995, and they informed us that our submission on LSTM, which you mentioned, got rejected. And what can you learn from that? You sometimes need a while until you realize whether something is good or not and useful or not.
It's a common story for many major methods in our list of tools in machine learning, for them to take, let's say, a good dozen years before they become mainstream.
That's right, yes. And actually, many people from Russia and the former Soviet Union, they were way ahead of their time. And I think Vapnik also had a hard time publishing his results on support vector machines and stuff. Until then, everybody suddenly was doing it. And even much older is the work by Ivaknenko and Lapa in 1965, who basically had the first deep learning networks. And back then, few people, I think very few people, realized how important that is. And today, everybody is using deep architectures like the ones that they introduced.
Yes, indeed. And, you know, this story with conferences, this classic story with the SIFT method, which actually probably motivated LeCun and other conferences for a new publishing model on conferences like iClear. SIFT was rejected for several years in a row, but in the year it was finally accepted, it became the best paper and most widely used thing in computer vision. So conferences and actually getting to the conference is a potential obstacle for some outstanding results.
Yes, this is absolutely true. Many of the most influential papers had a hard time overcoming these initial obstacles. However, on the other hand, one shouldn't conclude that everything that gets rejected is a great paper.
Certainly, certainly. But you know, false positives happen, and sometimes they are like tremendously false. But regardless, what do you think about some trends in machine learning nowadays? For example, about the way transformers are trying to replace LSTMs in natural language processing.
So actually, in many ways, transformers have really been very successful. And in some of these domains where LSTM used to be central, like, for example, translating from one language to another, in natural language processing, transformers are now really widely used and very successful. And we are also using them whenever we can use something like that. In fact, in the not so distant future, you are going to read something about transformers from us, from my lab, and also how they have a lot to do with what we published a couple of decades ago. And generally speaking, however, one should not forget that there are certain types of language processing where neural networks, especially recurrent networks such as LSTM, still are much more powerful. For example, just try to learn a context-free language or a context-sensitive language with a transformer, you will quickly fail if you really want to solve the full problem, while an LSTM doesn't really have any major problems in that. So I think all of these techniques you will have to use wisely. You will have to know their strengths and weaknesses, and there's a place for all of them.
Indeed. So no free lunch is real, right?
Yes. Well, the no free lunch theorem is, the way I like to think about that is, it is actually a corollary of a very simple insight from algorithmic information theory. And it goes like that. Suppose you have a training set, and let's call it X, and you want to learn from that training set X something about another set, about Y. Y could be the future, and X is the past, or, you know, any training set and any test set. Now, how much can you learn from any X about the Y? And it turns out that for almost all possible combinations of X's and Y's, you cannot learn anything from X about Y because there is zero algorithmic information between X and Y. What does that mean? It just means that if you try to compute through some program the Y, given the X, the program will have to be at least as long as the Y, no matter what you can find there in the X, which means that the Y by itself is incompressible. And if you know the X, you are not going to profit in any way by getting a shorter code for the program that computes the Y. Why is that? Well, because almost all strings that describe training sets such as X and Y, when you combine these X's and Y's and you get a long string that describes both of them, almost all are incompressible because there are, say, 2 to the n different combinations like that, where n is the size of the whole thing, so the number of bits you need to describe the entire thing. And there are only very, very few programs that have significantly shorter size, that have significantly fewer bits than that, which means that almost everything is incompressible, and almost all pairs of possible X's and Y's have nothing to do with each other, which means that no learning algorithm whatsoever can learn anything from X about Y, because there is no information in X about Y. However, in our friendly real world, in this universe, everything is very friendly in the sense that you can greatly generalize because everything seems to work according to these same recurring principles. So every electron seems to behave the same way, as if it is using the same subprogram to compute its behavior. Every elementary particle is doing the same thing. I can predict that if a certain chair stands in front of my, stands over there, then I will be able to see it again 1 second from now, and maybe even 1 hour from now, because there's so much regularity in the real world that we can exploit. So in the real world, we are lucky because many of the X's say a lot about the Y's. And if you have seen a video of falling apples, you can learn from that a lot about videos of falling peaches. And machine learning essentially is about exploiting these compressibilities in the data in friendly universes like ours.
So world models help us with various generalizations in the real world. By the way, I also wanted to ask a little bit. So you said that your group is already working on something curious involving transformers. So looking forward to it. But do you right now with your colleagues and students work on some really out-of-the-box new types of models? I know, like Gödel machines, or maybe something entirely new, entirely unexpected.
Let's not quite go there to the Gödel machine, which is very different from deep learning and which is mathematically optimal in a certain sense, which is not very practical yet. But let's just focus on a recent thing, which is also about reinforcement learning, where the goal is to maximize future expected rewards. And one of the intriguing little things that we found in recent years was that there is a very simple way of turning traditional reinforcement learning upside down and simplifying it. So normally in reinforcement learning, what you do is you have a controller which gets in the data from the environment and produces actions, and then you have a separate neural network which is looking at the actions of the controller and the inputs, and it is trying to predict how much reward is this system going to get if it is following this policy which is implemented by the controller, and what is the total expected future cumulative reward. So you need this prediction machine. However, there's a simple way of turning all of that on its head, of getting rid of the prediction machine, and you just have one single network, and you say, we give it an extra input. The one single network, the controller, gets an extra input, which says, which is a command, and the command says, get from now until 17 steps in the future, get a reward of at least 44. Okay, and then you just let it run and see what happens, and then you see that within the last 17 time steps, the system did not get a reward of 44, but only 33. And then you say, okay, let's retrospectively readjust the command, and let's say the command is changed now, get a reward of at least 33. And now suddenly what the system just did is correct. So now you can train it to take the input command, which is get so much reward within so much time, and you can correctly execute the actions according to this trained controller, and it has learned something about how to get so much reward in this time. And then you generalize from there. Now you say, once it has learned to respond correctly to all kinds of reward commands, you can say, now let's generalize, let's try something new. Let's try to get twice as much reward as we got so far within this time interval. And then you hope that your supervised learning system, because suddenly you can use supervised learning to train this reinforcement learning system, that it's going to generalize. And you say, let's now get a reward of 150 within 20 steps. and you see what happens. And if it fails, you still have a new training example where it can learn more about how the reward intake gets. So I think this very simple new way of reinforcement learning has a lot of promise, and it is especially interesting for things that will be of importance in the real world, where you have high-dimensional actions that are executed by the robots that you are controlling through reinforcement learning. Because traditional reinforcement learning, well, it works well with high-dimensional inputs, with videos and images, but it's really difficult to teach reinforcement learning systems complicated output actions where you have millions of muscles maybe that interact to produce certain desired results. So we are very interested in this thing called upside-down reinforcement learning.
Cool, really interesting. By the way, talking about reinforcement learning and other fields, what I wanted to ask you about is your opinion on the most underappreciated subfield of machine learning. You see, reinforcement learning was for quite a long time, more of an academic subfield, which quite recently started to emerge as more I'll say industry capable subfield with its methods. Of course, there are absolutely outstanding results with AlphaStar, AlphaGo, and similar. So the story with reinforcement learning is that it was more of an academic subfield, but now it finds its way into industry. What do you think is right now probably a yet underrepresented and underappreciated subfield in machine learning, which could be like the next reinforcement learning?
Yes. So in my point of view, the really challenging part is AI in the physical world and reinforcement learning in the physical world. Because what you have at the moment is reinforcement learning for video games and board games. Board games are rather simple in the sense that you can have a feed-forward network, and it looks at the state of the Go board, and the state is just 19 by 19 pixels, and some of these pixels are black, and some of them are white, and some of them have nothing. And from there, it is sufficient to have a feed-forward network that learns to respond to that situation with a new move. And it's not important to look at the history, how did I get into this state, because these board games are very friendly, they satisfy Markovian properties, and that makes reinforcement learning easier. So after AlphaGo and other board game players, people got more interested in this more complex scenario of video games, where you have to look at the history of things that happened in the past, where you then have to memorize important events in the past in order to execute good actions. And for example, the recent video game players by OpenAI and by DeepMind, what are they doing? They don't use the same thing that they used for AlphaGo, which doesn't work. No, they use an LSTM, which is trained by a reinforcement learning method called policy gradient methods. So policy gradients can be used to train LSTMs without a teacher to learn in reinforcement learning settings. Actually, 2007 to 2010, we had the first papers on this approach. However, then what you see in these applications to video games is you have billions and billions of video games, and in the real world, this doesn't work. In the real world, with real robots, you can have only a very small number of interactions from which you can learn. So the training examples in the real world are really tiny, and for that reason, you have to do things that are different from what you can do with video games. So in the real world, you want to minimize your interactions, and you probably want to build a predictive model of the world, a neural network which learns to predict the consequences of actions, such that you then can use this model to conduct mental experiments rather than true physical experiments. And this I don't think it's unappreciated. I think people understand that this is important. It just is, it doesn't work as well as, you know, all the supervised learning, which is on your smartphone and which is doing your speech recognition. So the really exciting part of AI in the physical world, like in the movies, that is not yet working well. And that's also the reason why my company is, Nascence, is really focusing on that part.
Really curious about indeed AI in the real world. So those small robots which clean our houses are pretty far from what we see in the movies. So your best recommendation for our community is to look into AI and in particular reinforcement learning in physical real world, right?
That's right, yeah. AI for the physical world, that's the hardest part of AI. If you look at the profits in AI of today, all of them are happening, or most of them are happening in the virtual world, on the World Wide Web, where some companies make 10 billion per quarter just by selling ads, by marketing, and that's fine. And it's good enough to make these companies pretty much the most valuable companies in the world, not counting maybe Saudi Aramco and stuff like that. But but it's just a tiny fraction of the world economy, and most of the world economy is not virtual. It's physical, and it's about making things, and it's about industrial processes and machines that make other machines, and all these things, products that are being made by humans mostly. So there is still 99% of the potential of AI which isn't tapped yet.
Really interesting. So hopefully our viewers and community members heard Juergen and are planning to have a deep dive into these topics, articles, tutorials, and workshops from recent years in conferences. My next question would be somewhere in between virtual and physical world. Let's say it's more on the virtual side. It's about beauty and in particular subjective beauty in art, because creative AI is also seeing rapid development in literally last several years. And how do you think? Is it possible to achieve greater results in creative AI, in particular, according to your paper, a simple algorithmic theory of subjective beauty, novelty, and I can't recall the whole name of the article, sorry. It seems that there may be either problems with formalization or maybe problems with models. So what do you think about the ongoing thing with the subjective beauty in AI?
Let me maybe first briefly summarize the very simple principles behind what you just mentioned. So how do you build an artificial agent that appreciates beauty and that is interested in the interesting things and bored by the boring things? It is very simple. So you have this controller, which can be a recurrent neural network where inputs are coming in, video and audio is coming in, and then you act in response to these inputs to achieve certain changes in the environment. And when you move your hand, then your video changes because the hand causes changes of the pixels as it is moving and stuff like that. And then there's another second network which is just looking at the actions and the inputs of the first one, of the controller. The second one is called the world model, the model of the world. And it's just learning to predict what's going to happen if the controller does that and that. So it's predicting the reactions of the environment. And now you can use the model of the world. If it's good, you can use it to plan ahead. So you can generate action sequences that lead to a lot of expected reward or promised reward. And if the world model is bad, at least you get new training examples to make it better. Okay, so what does that now have to do? So in the beginning, the model of the world is stupid and knows nothing. So what should the controller do? Somehow the controller should have an incentive to generate sequences of actions that lead to states of the environment where the model is still stupid and can learn something. curiosity, artificial curiosity. So you want to give the controller a reward for improving the model. Very simple. You want to give the controller a reward for executing experiments that improve the model, that yield data such that the model can become better. Now, what exactly does that mean? It means, what does it mean for the model to become better? In principle, the model, all it knows is the entire history of actions and inputs that it has seen so far. And it's somehow encoding this history. Why? Because it's predicting it, which means that it's compressing it, because everything you can predict, you don't have to store extra. So you have this compressed version of the history, and all you have to store are these deviations from the deviations between the observations and your predictions. And as long as the predictions match the observations, you get compression. Now, what should be the reward for the controller as the model is learning something that it didn't know? Learning something always means to have an insight about some principle that governs the data which you didn't have before. This always means that you can compress the data. For example, if you have a video of lots of falling apples, then once you understand gravity, you can predict how these apples, these orange blobs, are moving down. Maybe you cannot predict everything, every pixel, but many of these pixels, which means you can greatly compress. So the artificial scientist who sees videos of falling apples and suddenly can greatly compress the data which is being observed should get a joy signal, which is proportional to this insight, to the depth of the insight. So before the insight, the model needed so many bits of information, and afterwards only so many bits of information to encode the data. And the difference between before and after, that's the fun that you have, the joy that the controller, which is maximizing its joy, its reward, should get. And so the principle is very simple. However, it is still complicated for the reinforcement learning algorithm to maximize that kind of reward, because looking now at the controller, it has generated lots of things in the past, and some of these old data contain information about how to improve the model, and the model has a learning algorithm which is improving and always looking back at the past data, and suddenly there is an improvement, and there's an improvement, and the model can, maybe even in its sleep, or maybe even long after the observation, can greatly improve the compression. So there's a lot of compression progress, but it comes maybe after a long time. And so now it's hard for the controller to figure out which of my many actions in the past were really responsible for achieving this this joy signal, this insight of the model, which leads to compression progress and therefore to joy. So you have a huge delayed reinforcement learning problem, and the controller essentially must learn something about the learning mechanism of the model to do that right. And so here we still have a way to go to get the credit assignment right, such that the credit assignment can happen quickly and simply and is easy to solve. So there we still have something to do.
Okay, so I believe that was the part mostly about curiosity. But does this mean that if we apply curiosity and the same principle to beauty, and if we try to maximize the observer's expected utility of the beauty in one's eyes, then probably well, it either works not as expected right now, or on the other hand, maybe someone like Malevich with his big black square, which is totally predictable in terms of the picture one sees, has already maximized all of art.
No, he didn't. No, because this white or this black square was interesting only in the very beginning, when it was the first of its kind. You know, the first time somebody put a white paper, completely white painting on the wall, and he said, "White square on white ground," something like that as a title for that. that was maybe interesting, but afterwards it wasn't interesting any longer because people very quickly understand what's going on there, and they see another picture of that type, and it becomes uninteresting. It's immediately uninteresting because it's so predictable. So there's this big difference between what's beautiful and what's interesting. Beautiful, that's we could argue that this is only about object. So what is a beautiful tomato? If you have 10 tomatoes, then most people would say the most beautiful of these 10 tomatoes is not the one which has all kinds of stains on its skin and all kinds of deformations in its form. No, the most beautiful of these tomatoes is the one over there, which is very round and has perfect skin and whatever. And so why is that especially attractive? Because the description length of this tomato is really short in comparison to the description length of the other tomatoes, where you have lots of deviations from the expectations. So everybody who is looking at the tomatoes has something like a prototype tomato in his head, which he learned through lots of interactions with the environment and with real tomatoes. And so among the 10 tomatoes that are now in the visual field, the easiest to store is that beautiful one, because you only have to store a few tiny deviations from the prototype, and the lazy brain likes that. So if the new thing which comes in doesn't require lots of extra bits to be described, then you tend to say, oh, that's a beautiful thing. But it's not an interesting thing, because the most interesting tomato is a different one. It's the other one, which looks almost like a cube over there, which has a regularity, but the regularity is unexpected. So as long as you never have seen an almost cube-like tomato, you think, what kind of tomato is that? And you look at it and you see the regularity. It's not just a random deformation. No, it really looks more or less like a cube. Then this is a really interesting tomato, and you study it a little bit until you understand and know it and can learn nothing additional, no more bits about that, and then you also get bored by that one. But see, that is the big difference between beautiful tomatoes and interesting tomatoes. And this difference between beautiful tomatoes and interesting tomatoes also applies to all other kinds of objects, where you have the difference between beauty and interestingness.
Really interesting. So hopefully our colleagues from our internal community of machine learning art heard all of this, so they might design their next art pieces. Let us proceed then with more machine learning questions before we move to a broader scope. What do you think stops chatbots right now from reaching some more intelligent levels? Probably you remember there was a lot of hype with chatbots, which turned out to be mostly if-then rules. But nevertheless, these if-then rules were working properly most of the time. So what actually do you think stops chatbots from reaching these expectations?
I'm not a chatbot expert, but if I look at the chats on which chatbots are being trained, which are often chats between humans, then many of these chats don't look very intelligent. And maybe it's just a problem of the training set.
Yeah, indeed. You know, this case with Taya bot by Microsoft, which was released to the Twitter.
Yeah, well, unfortunately, that even was an LSTM back then. That was a couple of years ago, and Microsoft used an LSTM to train this Tay robot to imitate all kinds of chats that they found. And I think it worked great in China, but then they used it in America, and a couple of people there discovered that you can train it to become a neo-Nazi, and then it became really ugly, and they had to take it down.
Yeah, so basically issues with training sets. I believe this Taya bot reached a rank of a redneck neo-Nazi in less than 1 day. So,
yeah, exactly.
yeah,
And
and
it's embarrassing that an LSTM was involved in that, and so so maybe that is one of the not so golden experiences that you can have as a machine learning researcher.
well, regardless, there might be other chatbots with LSTMs, for example, those helping people in psychological therapy, which would also use LSTMs. Well, you get all sides of the coin.
Yes, yes. All kinds of technologies have upsides and downsides, and one has to learn to cope with that.
Cool. And with this question, we can actually move on to another really closely related topic about use and misuse of technologies. One of our community members wrote a question about broader impact statement at neurips. So for those of our viewers who are not familiar, a broader impact statement is an obligatory number of lines each researcher has to write about potential societal consequences, future societal consequences of his research. And our authors should discuss both positive but of course negative impacts. And my question to you, Juergen, is the following. What is your opinion about this whole thing with the broader impact statement, and in particular, should this be applied to absolutely neutral topics like really theoretical articles on maybe convergence boundaries of some estimators or some optimizers, quasi-Newtonian or like natural gradients and similar stuff?
Yeah, some of that seems a little bit overdone. However, it's really difficult to predict whether some theoretical result is not going to be important later. For example, in the late 1800s, people discovered all these theorems about prime numbers and the distribution of prime numbers and the zeta function and all kinds of exciting, very theoretical stuff, and nobody was able to do anything with that. However, 100 years later, suddenly these results about factorizing numbers and whatever, they became super important, and they came the center for a billion-dollar cryptography industry, which could be used by not only by people to protect their privacy, but also by secret services and so on. And now imagine one of these guys back then in the 1800s would have had to sign one of these broader impact statements. It reminds me a little bit of controlled fire. Controlled fire was invented about 800,000 years ago. And back then, people, the inventors of controlled fire, they realized that fire can be both good and bad, and you can use it to cook and to keep warm at night, but you can also use it to burn other people. And like AI, fire can even spread in the form of a wildfire without human ado. And when they realized all of that 800,000 years ago, they set up an ethics commission to debate the pros and cons of fire. And the final outcome, the final declaration of that commission said, yes, fire has drawbacks, but the pros outweigh the cons. And let's continue with the development of fire. And that's why we are here today.
So it seems hopeful that we will see less examples of prohibition of some articles because of the statements. By the way, how would you describe such a statement for your LSTM paper? Could you have guessed that many years ago, 23 years ago, that what would be its potential uses and misuses?
Well, I would have acted as a politician. I wouldn't have written that this thing is going to revolutionize speech recognition and machine translation and whatever, and secret services are going to use it to spy on you, and big companies, platform companies are going to use it to feed you ads. I would have not mentioned that even if I had thought of it.
But one knows, maybe there are articles with such statements about even optimizers, which can write that it might be used for an apocalyptic scenario with machines rising. But talking about politicians, you see, AI nowadays becomes more and more well known and often talked about from the mouths of world's leaders. World's largest top managers, they occasionally talk about AI. Recently there was a panel, an online panel, in which we participated with two presidents, which were also talking about AI. And how do you think, can this be risky or even dangerous that world's leaders might have not the very best understanding of modern AI and its capabilities as of today? In particular, these leaders tend to overestimate what AI is and what it can do.
I think important leaders, politicians all over the world, they both overestimate and underestimate what it can do. They overestimate what it can do now, and they underestimate what it might be able to do in 10 years when compute is again 100 times cheaper than today. So, since even scientists find it hard to predict exactly what's going to happen, I think it's excusable that that leading politicians also are not fully aware of all these possibilities. On the other hand, if you look back at the history of mankind, it was always driven not so much by the politicians, but by new technological developments, which then had their own dynamics, and companies used new ways of influencing people and whatever. The printing press 500 years ago was extremely influential in terms of setting the stage for the modern age, for the modern past 500 years. And politicians back then, they just reacted to what happened there based on these technological developments. So we will see the same thing in the future. Politicians will continue to react to technological developments that are happening faster than they can follow them.
As for this particular talk, meme on AI actually was birthed within open data science, that while watching presidents talk about whether AI can become a president, you should replace every AI word with the matrix multiplication and try to listen just how it sounds. Can matrix multiplication become a president?
A series of matrix multiplications,
Or a
plus the
series.
algorithm that organizes these matrix multiplications in a reasonable way, that might be able to become president at some point.
Well, one knows when we'll see it. But regarding this idea with, let's say, potential issues. Excuse me with my sound. Regarding potential issues with the politicians, quite an maybe not that unlikely today, but potentially very harmful and unfortunate scenario is that in some country there could arise like an AI equivalent of GDPR, Global Data Protection Regulation, General Data Protection Regulation, the one regulating data transfers and processing in Europe. And these politicians might just ban a ton of experiments on AI just because of their misunderstanding on what are the real capabilities and mistaking the current AI developments for the already somewhat sentient artificial general intelligence. How do you think, can this happen in some country? Like politicians will ban us from using and experimenting with GPT-6, GPT-7 and similar stuff.
Yeah. So there are certain fields of technology where an international agreement between superpowers can help to block further development. For example, in nuclear and technology, you need a lot of hardware and you need a lot of natural material that is hard to access. And that's where treaties between superpowers were able to stop the proliferation to a certain extent. But in AI research, it's much harder to do that because it's much easier, much simpler, and everybody can do it at home. So it's more like governments trying to prohibit alcohol. And yes, there are governments and have been governments in the past who try to stop the consumption of alcohol, but they weren't really successful anyway. And so I don't think that there's any instance in the world that can successfully interrupt the curiosity of all these researchers who would like to further improve their AIs.
Mm-hmm. Well, let's hope AI will not become the next alcohol or drugs banned for international use.
I know that was a bad example, but you get the gist of it. So it is not possible for a single instance that is known on this planet to stop the further progress of technology in that field, because
there will always be a country where it's not regulated, and this country will just move straight to the moon.
Yeah, obviously, even if many people agree that AI should not be used for developing better weapons, it's going to be done because there is not us, humankind, which is consisting of billions of people. They all have the same opinion. No, humankind consists of many different people with different opinions, and the Chinese will say if we don't do it, and the Russians will do it, and the Russians say if we don't do it, the Americans will do it, and the Americans will say if we don't do it, the Israelis will do it, whatever. So there will always be an excuse to use AI even for purposes that are not generally encouraged by everybody.
Cool. Also, a fresh question from our chat while we are talking on AGI and briefly touched upon it. How do you think, is it possible to construct an error function for AGI so that it would find an optimal behavior to help people, but not to somehow maybe potentially threaten them, even just with the possibility that it can take their jobs? How would you define an AGI error function, or rather reward function?
This is reminiscent of what Isaac Asimov had back then in his science fiction novels, The Three Laws of Robotics. And even the first law, when I read that, I thought, this is fun, but it's not logical, it's not feasible. So I think the first law said more or less, no robot is allowed to harm any human or allow through inaction that some human comes to harm. And now to implement that law, you have to implement a super intelligence which is able to predict all the consequences of its actions. And in this universe, I think it's not possible to build anything like this. And even the implementation of the first half of the first law, which is no robot may harm any humans, seems infeasible because it means this robot must have perfect pattern recognition and it must be able to distinguish the other robots from the humans. And Asimov's stories are a lot about robots that look like humans, androids that look like humans, and they are very hard to distinguish from the real thing. So even from a logical perspective, it seems infeasible to implement such a law in a way that is sound.
So that was about the AGI. Also, talking about broader topics of machine learning, our community members really wanted to ask, in particular with the comments like asking for a friend, what do you think about the possibility of AI winters or maybe some similar, let's say, effects? Because you see, AI is cyclical as a field, so there were ups and downs. We are clearly right now on the upside. So the question is about your views on any potential AI winters, because once again, the field seemed to be cyclical previously in its 50-year history, more than 50-year, to be honest. And we are right now on the probably highest point of the field and it has ever been and has ever seen. Could there be a drop down somewhere, or the only way is to the moon, let's say?
It seems very unlikely. If you look at the field of printing, it also had its ups and downs, 800 years after Christ, suddenly we had the first printing, woodblock printing in China, but then it also stayed there for a long time and didn't really conquer the world. And then 500 years ago, 550 years ago, the modern printing press, Gutenberg's thing with these simple letters, that was again an upswing, and since then we never have looked back because printing is now just so fundamental to everything we do, and we look around, everything is printed. It has become a part of society. We don't even talk about it any longer. The same is going to happen for AI. For a while it was sexy because it was still new for the first time in the eyes of many people who for the first time had little AIs on their smartphones for speech recognition and so on. But now it's permeating the modern world more and more. And in a sense, although its impact is growing, it's also kind of vanishing. Just like we don't talk about printing any longer, we won't talk about AI any longer as it is permeating every aspect of our civilization.
Got it. Got it. So we are almost out of time, but we still have a few personal questions. So the very first one our community was really interested is where can they buy a hat just like your iconic hat from all your photos in all the journals?
My hat. Tom Gruber has my hat. Background, Tom Gruber is the founder or co-founder of Siri before it was bought by Apple. And a couple of years ago, I was at a conference in Asilomar in California where Tom Gruber wore a cap just like mine. And so I took mine off and people asked me, where is your hat? And I told everybody, Tom Gruber stole it. This conference, by the way, was also fun in other ways. It was about beneficial AI, or BAI, beneficial AI, and it took place in a resort where they also had other conferences running at the same time. And breakfast was in a building in the center of this resort where the tables for the different meetings were marked by signs with labels. And I looked for the BAI label, Beneficial Artificial Intelligence label, and I found it, although it was misspelled. It didn't say BAI, but it said VAI. Okay, so I sat down at this table, and it soon turned out that these guys at the table, they knew nothing about AI, but they knew a lot about guitars. And it turns out they were with Steve Vai, V-A-I, who is a famous rock guitarist. And he gave his annual seminar there for his disciples. And in the evening, he played on stage with the guitar, and his disciples got close and used their smartphones to film his fingers while he was playing, working the guitar. And to blend in, I did the same. It was fun.
Oh, that's indeed a very lucky coincidence between conferences. Our colleagues told us stories that probably last year's KDD was co-joined with the conference with Jehovah Witnesses. So they had in the same building KDD in one end, and this I'm not sure is it offensive or not to call these people cultists, because in Russia Jehovah Witnesses are considered a cult. And yeah, our friends and community members and colleagues told us that it was a very unusual scene to look for. Another thing our community members are really interested is what is your recipe for staying fit? Like, what is your workout?
So I do work out regularly to have a basis. The mind needs to build on a healthy body. The workout is important, but the diet is also important, and in fact, I like the diet of Manfred Nerlinger. I'm from Bavaria. Manfred Nerlinger is also from Bavaria, and he's a weightlifter. And he used to be the second strongest man in the world, behind a guy from the Soviet Union. And Manfred Nerlinger, he was able to reduce his weight from 180 kilograms down to 150 kilograms. And he achieved that using his peaches diet. The peaches diet goes like this. You can eat what you want, but no peaches.
Great. So hopefully our ODS sport chat is happy to hear the recipe for a healthy body, healthy mind. Probably the last few questions, last two of those. What is, if you could send yourself your 18-year-old self just one note with some knowledge from today, what would it be?
So if I could send a message back to my
18-year-old
teenager, I would send a message saying, it's just 10 lines of code, stupid. What you want to achieve is just 10 lines of code.
That's motivating. And finally, what's your Christmas wish for artificial intelligence field in 2021?
Peace and prosperity.
Peace and prosperity. Great. So it was a great pleasure to talk with you today, Juergen. Thank you very much for so many detailed answers. I hope everyone in our community got a lot of inspiration. Just one final thought. If you liked some question most of all, could you choose one so that we could award this person with merchandise like these metallic things?
Yeah, the most important question obviously was the one about the cap.
Yeah, the cap. Okay, deal. So this person will be awarded. Once again, thank you very much from all of our community. It was a great pleasure. And wish you a great Christmas in you're right now in Switzerland, right?
That's right. Thank you, Alexei, but thank you also, community out there, for sending questions and for listening right now. And I hope you will have very pleasant holidays.
Great. So once again, thank you, Juergen, and thanks from the whole of our community.
Thank you. Bye-bye.
Bye bye.